Bro, I made the resources that I
There's three kind of big types of problems that I haven't gone over yet. First is similar triangles involving shadows. So this is very specific type of problem. It's easier than cones, but it uses the same concept, but it's also the application is also very specific for this problem. So that's the first one I want to do. The second one I want to do is cylinders. Cylinders and cones have very similar formulas, but we don't do similar triangles for cylinders. But there are going to be potentially extraneous information for cylinders that throw students off to kind of see if students will fall for setting a problem up like cones. So in a sense, it's easier, but it's also harder because of the distractions that can come with information given from cone problems. And the third is your homework. You guys had a problem that dealt with rate of change of theta, and we haven't quite gone over rate of change of theta. So we'll definitely do one of those. And if we have time, we can look at the homework that you guys were working on yesterday. So those are three things I want to do today. Let's start with similar triangles, shadow problems. So page 14. So here's our diagram. It's always going to look like this. So we have a man who is 6 feet tall walking away from a lamppost. So this person is walking to either towards the lamppost or away, but we know is walking away at a rate of 5 feet per minute. The lamppost is 20 feet tall. So here's the lamppost. And the person casts a shadow on the ground in front of them. So the light from the lamppost is going to cast the shadow on the ground. So Y represents the length of the shadow. Okay, this is the length of the shadow. How fast is the shadow growing when the person is 30 feet from the lamppost? And part B, how fast is the tip of the shadow moving when the person is 30 feet from the lamppost? So I wanted to see that there's a triangle within a triangle, and the tip of the shadow in relation to the person's height is going to form the small triangle. And the large triangle is formed by the tip of the shadow all the way to the ground beneath the lamppost, okay, or the base of the lamppost and the top of the lamppost. So here are the dimensions of our similar triangles. Okay. We're going to start off by creating an equation that relates the different side lengths to each other. So we know that that the 6 and the 20 are proportional to each other. And we also know that the base and the large base are also proportional to each other. So I can say this. I can say the height of the small triangle is to the height of the large triangle as the base of the small triangle. What's the base of the small triangle? Y. Is to the base of the large triangle, which is what? Good. Not x times y, it's x plus y. So and I would say that's the hardest part. If you can set up the proportion equation, then the rest would feel a lot more straightforward. Okay, I'm going to cross multiply so I can get this equation down to something easier to work with. So I'm going to distribute that 6 through. Combine like terms. And next, I'm going to find the derivative. So I have an easy equation to find the derivative. Remember, time is our independent variable here. So what's 6x's derivative? Good, 6 dx dt. And then the 14y becomes what? Yeah, 14 dy dt.
We also do 3x equals 7 1, 3 dx equals 7 dy dt.
How are you getting the 7?
Dividing by 2 amounts.
Oh, got it, got it. Yes. I haven't reduced the numbers, but yes, you can reduce those. So let me define what each of these variables mean. If you always set up your diagram like this, your x is on, is the large portion and y is the shadow. Then this is how we can define these variables. So dx dt is going to be how fast this distance is changing between the person and the lamppost. So we think of that as the rate of the person walking, either away or towards the lamppost. Next is dy dt. dy dt is the rate of change of the length of the shadow. Okay. So as he's walking away, that shadow length is going to get larger. If he's walking towards, that shadow length is going to get smaller. And finally, there's a rate of change of the tip of the shadow. So the tip of the shadow is how fast that tip is moving in relation to the ground. And that tip of the shadow is getting impacted by both how fast a person is walking and how fast the length of the shadow is increasing. So both those rates are going to be on top of each other. And so that's going to cause this to be the fastest. So once I find dx dt and dy dt, I can add those together, and that's going to be the rate of change of the tip of the shadow. So let's go back and look at the problem here. Can we assign some values to variables? Okay, part A. Let's see. Okay, man is 6 feet tall. We have that already. He's walking away from the lamppost at a rate of 5 feet per minute. Okay, so that's dx dt, right? And it's positive because he's walking away, so that x is growing. So we know dx dt is a positive 5. And that's all we need, because if I can plug 5 in here, I can solve for dy dt. If I can solve for dy dt, then I have my rate of the shadow length. And if I have both dx dt and dy dt, then I can find the rate of change of the tip of the shadow. So dy dt is 15 over 7. And that is the rate of change of the length of the shadow. And then part B, I can just add the two rates together, and that'll give me the rate of change to the tip of the shadow. So if you have the diagram in front of you, and if you know what each of the derivatives mean, then this is a relatively easy problem, but it just requires us to practice knowing how to set up, because this problem, these steps are kind of very specific for this problem alone. So, but it's shown up on AP exam, so we want to make sure we go over this type of problem as specific as it is. Any questions with those steps? So you're always going to set up your diagram the same way. These pieces will always be the known information, and then the x and y will always be the unknown. And then you're always going to set up your proportions in the same way, cross multiply, find the derivative. dx dt is always the rate of change of the person. dy dt is always the rate of change of the length of the shadow. And then add those two together, that's always going to be the rate of change of the tip of the shadow. All right, any questions with? Okay, you guys want to try number 2 and see if you can go through a problem on your own with all the steps so that I can be convinced that you're comfortable with this. All right, so try number 2. Page 14, number 2. Mistakes I've seen in the past, students would say x over x plus y because that feels more like you want to start with x in it. But x doesn't represent the full base of any triangle. So if you want to set it up this way, then you need to have y over x plus y. And why is dx dt negative? Yeah, that's causing that x distance to decrease. So since x is decreasing, we want dx dt to be negative. So it's not difficult, but you just have to learn the steps for this very specific problem. Right? And all these things are really just for this problem alone. Any questions here? Yeah. Well, as the person is walking towards the lamppost, his shadow is going to be decreasing. Yeah. So the further he walks away, the longer that shadow length is going to be. Yeah. Are we okay with shadow problems? All right, next up, I want to talk about comparing cones and cylinders. So this is page 15. We did the cone problem above. Let's talk about the cylinder problem below. Okay, so here's number 4, page 15. All right, problem says the coffee pot has the shape of a cylinder. Now, cylinder has this formula. V is equal to pi r squared h. And if you look, it feels a lot like cone formula. Cone is pi over 3 r squared h. The fact that their formula looks a lot alike, we might assume that the process will feel similar, but it's going to be very, very different, and easier too, okay, for cylinders. Coffee pot is shaped of cylinder with a radius of 5 inches, as shown in the figure above. Let h be the depth of the coffee in the pot, measured in inches, where t is measured in seconds. The volume is changing at a rate of -5 pi root h. So I can just assign this to be what? dv dt, yeah. The volume of the cylinder is, okay, they gave us v equals pi r squared h. Find dh dt as a function of h. Okay, so I want to kind of draw the important distinction between cones and cylinders, at least for us, for our problems. Okay, let's talk about first the radius and the height of the water inside the cone tank. And let's say water is coming in. Right? Is the radius changing of the water level? Yes, right. As water's coming in, that radius is going to grow larger and larger, right? Because that cone is going to get, the dimension will keep expanding in both directions, right? It's going to get wider and it's going to get taller. So both the radius and height are changing, and that's why we have to keep both as variables. Okay. Now, let's talk about the radius and the height of the water level inside a cylinder. Let's say water is, what's water? Water. Sorry, the coffee is draining out or being removed. Is the height changing?
Yeah.
Yes. Is the radius changing? No. So that's the big distinction. Okay. The big distinction is that the radius is a constant. And if the radius is a constant, there's no need for us to hold on to that variable. If there's no need to hold on to that variable, our derivative will be a lot easier. There's no need to do similar triangles. The issue that students experience with cylinders is that sometimes the problem gives you additional information that you don't need. It starts giving you, the height of the water level and the height of the container, and it starts making you feel like, okay, I got to use all this information somehow, and you start putting it into proportion like cones, and then there's no need for that, right? So as soon as we know what the radius is, we can replace that number for radius, because we know that no matter where that water level is, it's going to stay the same constant radius of 5 inches. Okay, so everything we need is in front of us. We just have to plug stuff in, right? So our V, our volume, is just pi r squared times, pi 5 squared times h. And we were able to quickly rid ourselves of one of the variable because it's never going to change. We couldn't do that with cones. We had to hold on to those two variables. And that's why we had to do similar triangles. We have to get one variable in terms of the other. But here, the variable just disappears. So we should have a relatively easy derivative to do. V equals 25 pi h. Let's go ahead and find the derivative. V becomes dv dt. 25 pi h becomes 25 pi, right? That's the coefficient times what? Times dh dt. Okay. We should be able to plug everything in. Replace dv dt with -5 pi root h and solve for dh dt. And because dv dt has h in it, we just have to hold on to h in our answer. Okay. Replace dv dt with -5 pi root h. Divide both sides by 25 pi. We reduce, and our dh dt is -root h over 5 inches per second. So cylinders should feel easier than cones. And if they give you a whole bunch of information that you don't need, you got to ignore that information and just focus on, okay, as long if I can get to the radius, I can just go ahead and simplify my equation. I don't need the height of the water level or the height of the container. If they provide that information to you, you're going to ignore it, right? It's great for cones, but it doesn't matter for cylinders. Right, let me do a problem with you that involves rate of change of theta. So let's go to page 21. This is similar to 38 that you guys were attempting to try yesterday. Okay, so this is a ladder problem that we've been doing from before. It's just that now we're trying to find the rate of change of theta instead of finding the rate of change of the x, the height, or the length of this triangle. So a ladder 5 meters long is leaning against the wall. If the lower end of the ladder slides away from the wall at the rate of 0.5 meters per second, at what rate is the inclination theta of the ladder with respect to the ground changing? Sorry, something got cut off. When the lower end is 4 meters from the wall. So let's set up our triangle here. I have information about this side. I'll call that x. And anytime that there's a constant given, I always want to take advantage of it. Because we prefer to, we're going to set up a trig equation that relates two sides and theta. And the reason that we want to take advantage of a constant is because the derivative will be easier. There's no need for quotient rule. And also, we want to target the information or value that we have information about. So we don't have any information about the y component. We do have information about the x. So your first setup is trying to create a trig equation that relates the two sides and the theta. So what trig equation will allow us to hit theta, x, and 5? Good. So that's our starting equation. Other starting equations that we've done before have been Pythagorean theorem, or volume of cones, or volume of spheres, or area of squares. Our starting equation here is the trig equation that relates theta with the two sides. So you guys said cosine, so we can say cosine of theta is equal to x over 5. So this is what we're trying to find the derivative for. Maybe make it a little bit cleaner on the right side. You don't have to do this. I just feel like students tend to like looking at a coefficient instead of a number below the variable. Okay, let's go ahead and find the derivative. Remember, this is related rates. Every variable gets impacted by time. So cosine of theta becomes good. 1/5 x becomes 1/5 dxdt. Yeah. All right. Do we know what dxdt is? 0.5, because it says the lower end is sliding away from the wall. So we know that x is growing at a rate of 0.5 meters per second. So that's great. What are we looking for? d theta dt. All right, so really the only missing information is what? Right, so here's the thing is that the issue that students run into is that they try to find theta, and we don't know what theta is, but it's okay. We're going to find a bigger replacement. We're going to find a replacement for this entire sine of theta. So if you try to find theta, then you're going down a more difficult path. We want to find just the ratio of this triangle at this moment in time. Okay, so we're replacing more than theta. We're going to replace the entire sine of theta. So I'm going to step to the side here and just draw a triangle with this moment in time filled out. So we know that this is 5. When the lower end is 4 meters from the wall, so this is a moment in time when x is 4, which means that the y is going to be what? 3. And then based off of this diagram, what's sine of theta equal to? 3/5. And that is the replacement we're making. So that's really the main challenge of these problems is recognizing, okay, I'm not trying to find theta, I'm trying to find the entire ratio. So I'm going to step to the side, fill out all the sides of a right triangle. If I don't have all 3 sides, I'll use Pythagorean theorem to find the third missing side, and then find the ratio that's associated for my derivative. So 3/5 goes in here. D theta dt is the unknown, and dx dt is 0.5. And then your units of measure is always radians per time unit. Okay. Any questions there? Okay. Let's do one more of these so that you guys can kind of practice this type of problem. But let me kind of go through the big picture here. The summary of this problem is anytime we're looking for theta, draw a triangle, find the 2 corresponding sides that will relate to your problem. And anytime you can take advantage of a constant, you can avoid quotient rule. And then you're going to create a trig equation, either sine, cosine, or tangent. After you create your equation, then you find the derivative with respect to time. And then you're always going to replace your resulting trig ratio with, or your trig expression with a ratio. All right, so I found another one in your packet that we can try. So this is on page 23, number 2. Okay, read the problem, see how much you can set up. The diagram is already drawn for you, so that's nice. And so my trig equation is sine of theta equals x over 2, which is the same thing as sine of theta equals 1/2 x. Find the derivative. Sine becomes cosine theta, d theta dt, 1/2 x becomes 1/2 dx dt. The difference here is that we know what d theta dt is. We're just solving for a different variable, trying to solve for dx dt. But we still need to figure out the ratio for cosine theta. So off to the side, I drew another triangle. My x is 1, which means Pythagorean theorem can help us get to that root 3. You know, c squared minus b squared equals a squared. I can take the square root of 3 to get to root 3. And so cosine theta is just root 3 over 2. So that replaces my cosine theta. And now I'm just off to trying to solve for dx dt. Okay, last problem that I wanted to try is this is a free response question from the past that has both a cone and a cylinder in it. So this is on page 17. This is an old FRQ here. So the cone, you're going to need similar triangles, but for the cylinder, you're not, because the radius is never changing. So read the problem and see how far you can get. So you did cosine theta is 1/2, but the theta is down here, so it's going to be adjacent to this. So this needs to be different ratio.
Oh, so that again, so this is very. Yeah. So that's what we're saying. Okay, yeah. Thank you. I yeah, I just mixed up signs.
Yeah, sure. I set up my proportions for my cone. R over 4 equals h over 12. The problem says write a volume equation in terms of h. So that means I want to remove r. So I solve for r in terms of h, and then I can put that into part A. So part A is not asking for the derivative. They just want you to build the volume equation so that part B can jump directly to the derivative step. So once I get r equals h over 3, I can put that back into the volume equation and then just try to clean up that volume in terms of h. And now this gives us a starting point for part B, which is finding the derivative doing related rates. So no related rates yet for part A. We're just getting ourselves ready so that the right side only shows one variable. Okay, part B, at what rate is the volume of water changing when H equals 3? So now I can find the derivative. D becomes dV dt. We find the derivative for H. dH dt shows up. Start inserting values into variables. So for the cone, why is dV dt negative? Yeah, volume's decreasing, right? So in a related instance, what do you think the dV dt is for the cylinder? Right, yeah, so it's gonna be positive 9 pi, right? So if the rate of change of the cone is decreasing by negative 9 pi, then that means the cylinder is increasing by positive 9 pi, right? They're gonna be related to each other because that water from the cone is falling into the cylinder. So we have to make a slight adjustment for part C. The dV/dt from part B is related to the dV/dt from part C. So the formula for cylinder is V equals pi r squared h. I use a squared y so that it doesn't conflict with the variables that we've already used. You don't have to, you can use r and h again. But the idea is that if I can find the radius of my cylinder, then there's no need to hold on to that radius variable anymore. And the way that we get to that information is they tell us that the base of the tank has an area of 400 pi square feet. So they're telling us the area of the circular base. And if I have the area of the circular base, I can work backwards and figure out the radius of that cylinder. And if I have the radius of the cylinder, then I can plug that in, and there's no need for me to hold on to that variable. So you can just say V is equal to 400 pi h if you want. I used y to represent the height of the cylinder. But just like from the previous problems that we saw, that there's no need to go through similar triangles. As soon as we get rid of the radius, we have a much easier derivative. V becomes dV dt, y or h becomes dy dt or dH dt. And then the dV dt is just pulled from part B just to make it positive since water is now entering into that cylinder tank. And then we just solve the dH dt, which is 9/400 feet per day. Okay, so tomorrow we have one final topic to go over, and that is L'Hopital's rule. That's quick and easy. It won't take but like maybe 10, 15 minutes. And then I'll give you the quiz review, and then we can start working through the quiz review. So we'll start quiz review tomorrow, quiz review Thursday, Friday, we'll start the new units. Obviously not going to be on the quiz, but gives you the weekend to study for the quiz. And we can maybe spend a little bit of time Friday looking over more problems, and then your quiz is Monday. Help session will be Thursday morning and Monday morning. All right, come with your phones. Check your calendar, there's homework tonight.
Carolyn.
Always.
Hey.